Okay, today we are going to go on our pursuit of polynomials of a higher degree. So we've already talked about linear polynomials and quadratics, which are degree 2. We're going to go into cubics and quartics and, higher ones, 5th degree, 6th degrees, and so on. So our main goal at the end of this lesson, hopefully, is that you can take a function like this. It's a nice long function, and you can graph that, sketch it without your calculator. That's our goal today. Okay, so we're eventually going to get there. Let's review real quick a couple things. Polynomials, this is what we're going to deal with today. It's a combination of a bunch of monomials. The degree of the polynomial is the highest exponent. The leading coefficient is the number that's in front of that x that has that higher power. If you wrote it in standard form, it would be the first number. Okay? It's not always in standard form, though. Make sure you remember that. So that's your basic polynomials that we already talked about. We're going to review just real quick about how to transform monomial functions. So we have talked about the parent function, x squared. We know it's a parabola. And we've talked about how to transform it when you're adding or subtracting to parts of it or multiplying to parts of it. So in this case, the x is adding 1, so we know that that is moving the graph left 1. We are multiplying outside, not in here with the x, but out here. We're multiplying by 4, so that's a vertical stretch by 4. Okay? So it's going to pull it real skinny. It's going to pull it up, and it makes it a little bit narrower. We can also find the y-intercept, and this is something that we have to be able to do to achieve our goal in the front. You want to find the y-intercept, and if you remember by definition in Algebra 1, the y-intercept is the point where the x-coordinate is 0. So if I want to find the y-intercept, I'm going to put a 0 in for the x. So 4 times 1 squared is 4. So my y-intercept is 4. That's an additional point that we can put on our graph. So our vertex of this graph is -1, 0, because we're shifting left 1 and we didn't go up at all. So our starting vertex was always here. We are moving it to left 1 and up nothing, so we're right there. And then the y-intercept is at 4, which is here. And remember, it has an axis of symmetry, which puts the other mirror point here. So that's going to make a very, very, very skinny parabola. So we should all be able to do that at this point. Okay. Now over here we have a quartic, a 4th degree, x to the 4th, that was transformed. And we haven't talked about these yet, but conveniently, an x squared graph and an x to the 4th graph, basically the same. They look the same. They're the parabola shape. Okay. The width is a little different because of the power, but the basic standard shape is this. That's an x to the 4th. That's an x to the 6th. That's an x to the 108th power, okay? They all basically have the same U shape until you start adding and multiplying and doing things like that. So we're going to transform this guy just like we did before with the squared one over here. We are moving this guy right 2 because of the -2 here. We are going up 5 because of the +5, and the negative in front, if you remember, we'll flip it upside down. So our vertex is at 2, 5. Now, that's the only point we have, so we're going to look for our y-intercept. And again, our y-intercept is found by plugging in 0 for the x. So this is -2 to the 4th is a +16, times the negative out front is a -16, plus 5 is -11. So that's clear down here. And my mirror is here, so I'm going to go 2 off the mirror. It's going to be right here. That's all we need to sketch our graph. Shape guy. Okay? It's upside down U. See me? Upside down U. So that's just kind of a review in adding a fourth degree. The sixth degree would be the same, and so on. Now, combining monomial functions. So when you start adding the two functions together, so we have an x cubed, which is the blue graph, and an x squared, I'm sorry, just an x, which is the red graph. That red graph is going to pull the cubic, and so it looks like the green graph. Changes the shape a bit. It pulls that inflection point, so it's a little straighter. Over here we have a negative x, so the line is a decreasing line. And again, it's going to change the shape when you put those together. So now that's creating those hills and valleys, those max and min points with that particular combination. Okay, so it just all depends on whether you're adding or subtracting, if you're adding an x or x squared or so on. So it comes to be a lot of neat little ups and downs in the graph. Here is a rule, a law, if you will. The polynomial function of degree n has at most n minus 1 local extreme points and at most n zeros. So that means if I'm looking at a cubic, you can have at most 2 points of extreme, like a high or a low. Okay? And it has at most 3 zeros. And you'll see what we're saying here in a minute. Like if I draw something here. What function could this be? So if you look, it's crossing the x-axis at 4 places. So this has to be at least a fourth degree. Has to be at least a fourth degree. It can't be a cubic. If it were a cubic, it can only have up to 3 zeros. So this one already has 4, so I know it has to be at least a fourth degree or higher. And if you look, you have 1, 2, 3. So that would be n minus 1. So you have 3 extreme maxes or mins. All right. So this is more likely a fourth degree. It could be, if it were to come back up, we could maybe say it was a fifth degree. But most of the time, when you see those arrows, it means we're done. We're done graphing. So I would say this is a fourth degree. Okay. If you're looking at cubic functions and quartic functions, just look at these for a minute and see if you notice something that's the same with the top graphs and the same in the bottom graphs. So the top graphs have something in common and the bottom graphs have something in common. And they're all the top graphs are cubics. So some of them are straighter, some of them have more extremes. And the bottom graphs are all quartics or degree 4. And again, the middles kind of look all different. But what do you notice it's the same? Okay, in the top graph, the end behaviors, how that graph starts and how that graph ends is opposite. So the end behavior is either, starting low and going high or starting high and going low. In the bottom set, the end behaviors are the same. You either start high and end high or start low and end low. So the end behaviors of a quartic function equal. The end behaviors of a cubic function are opposites. Okay, so that's an important thing to keep track of. Now, what's neat is every odd degree, whether it's a cubic or a fifth degree or an 11th degree or so on, any odd degree will have that same idea of opposite end behaviors. And it all depends on that leading coefficient that I said was going to be important. If you have a positive leading coefficient, your end behavior is going to look like a positive line, which is the most basic odd exponent, odd degree graph you can get. So it doesn't matter what's going on in here in the middle. We are just looking at the end behavior because you could have all sorts of hills and valleys and all sorts of stuff in the middle. We're looking just at end behavior. So if it's a positive leading coefficient, It starts low, the end behavior on the left where x is going to negative infinity is negative infinity. And the end behavior on the right is going to be at positive infinity. And if the a value is negative, it's exactly opposite. This graph's going to start high at positive infinity and it's going to end down at negative infinity. All right? So keep in mind that limit notation, you have got to start seeing how to write that. It's really, really, really important. Take a minute. So this says the limit of the function f of x as x goes to infinity. That means on the right side of the graph where the x's are big. The graph's height is equal to infinity. So remember, the limit or end behavior, they're just saying, hey, what's the height at a specific side of the graph? This one says, what's the limit of the function as x approaches negative infinity? On the left side, what's the height going to? And you can see it's going down. It's going to negative infinity. So know how to write that limit notation. Okay, very important. A little different in this book than the previous course. So you have to learn a new way of writing it. If it's an even degree, just like the basic quadratic, we're looking at just the basic quadratic. So a positive a, if you remember, the quadratic's opening up. So an even degree is going to be the same in behavior, both negative or both positive infinity. If it's a negative a, your quadratic is opening down. The same with all the higher even degrees. Okay, so that's in behavior. So if you're looking at a polynomial, the only thing you need to look at for in behavior is the leading coefficient and what's the degree. That's it. And we can write down the in behavior. Okay, so we're going to try a couple. So this is the only thing I care about. None of this other stuff matters. None of the other stuff matters. We are looking at a positive odd degree. I don't even care that it's a 3. I just need to know it's a positive odd. So it's going to have the same in behavior as my positive line linear function. So the limit as x approaches negative infinity of the function f of x. What is the height approaching on the left side? It's approaching negative infinity. On the right side of that line, it's got to go opposite. So it would be going to positive infinity, low to high. Remember, it doesn't have to be in standard form. So if you look, this is supposed to be our leading term, if I were to rewrite that. So we have a negative even degree. So I'm thinking of the negative quadratic. So the limit of this function g as x approaches negative infinity is, if you look here at our quadratic, the height is going down, down, down. So it's negative infinity. And it's going to be the same for when the function goes to, as the x goes to positive infinity. Okay? It's that easy. Okay? Don't get bogged down with, what about, all the x. It doesn't matter what the other x's are doing. The other x's are creating the hills and valleys in between the in behaviors. We are only looking at in behaviors for right now. Okay? So here's another example. You guys can try. Take a second. It's a negative odd degree. So that's going to be the negative line. Really, 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 and I know you were doing these examples over and over again, practice writing the limit notation. So as x goes to negative infinity, that's the left side of the graph. The graph is going up, so that is positive infinity. As x goes to positive infinity on the right side of the graph, it's going down. They should be opposites if it's odd. Okay? All right. Finding the zeros of a polynomial function. So we're going to do this algebraically because we're not touching our calculators. You have to factor. And I know some of you don't like to factor. I get it, but you got to know it. You got to be able to factor. So the first thing you should always, always, always look at when you're factoring is there a common factor for me to pull out? In this case, you have an x in common, so we're going to pull that x out. And we have an x times a quadratic, and you should be able to factor the quadratic. Most of the ones we're going to be dealing with here are going to be pretty basic quadratics to factor. You have x squared, so it's got to be an x and an x. And then we're looking at what multiplies to 6 but subtracts to -1. So what two numbers multiply to 6 but will subtract to 1? And that is going to be, we need a -1, so it's going to be a 2 minus a 3. So 2 minus 3 is -1. 2 times -3 gives you that -6 you need at the end. Okay? And we want to find the zeros. So we're going to set each of these guys equal to 0. So the first term is x equals 0. It's done. There's nothing else to do. The next factor, x plus 2 equals 0, gives you an x equals -2, 0. And x minus 3 equals 0 gives you an x equals 3 for a 0. Now, we have 3 zeros. If you look at this in standard form, and I put a 0 in for x's, my y-intercept is also 0. I'm going to look at the degree. It's a positive odd degree. So I know the graph starts low and goes high. So all this information is going to let me sketch this graph without our calculator. So here we go. It's not the neatest graph, but we're going to be okay. 0, -2, and 3. The y-intercept is 0, so we've already got that graphed. We know it starts low and goes high. So we're going to start down here. We're going to go up, hit that x-intercept, hit the other x-intercept, the third one, and there you go. We're not so concerned about the max or the min, where they're going. Are they going too high or whatever? Just get the x-intercepts, the turning points, and then behavior right. Okay, so that's what we want to be able to do. Plot our x-intercepts, understand our end behavior. So am I starting at the bottom of the graph, or am I going to start at the top, and where am I ending on the right side? Okay, so plot what points you can, which are going to be your x-intercepts and y-intercept, and then connect them using your end behavior knowledge. So let's try another one. We're going to factor this guy. It's just a quadratic, so this is going to be pretty easy. You already have it in your head what it looks like. Factors of 8 that subtract to 2 would be a 4 and a -2. We should be able to get those zeros without setting them each equal. So x plus 4 equals 0 gives me -4, and x minus 2 equals 0 gives me a 2. My y-intercept is -8. It's always this constant when you're looking at it in standard form. And then we can graph. It is a positive even degree. So that tells me it's going to start high. And curve down, hit that y-intercept, come back up and hit the other x-axis, or x-intercept. Again, we could find the vertex if we wanted to find that extra point, but we don't need to. I just want to look at a sketch. Right? Okay, so let's move on. We're going to keep doing these throughout the lesson. So the multiplicity of a 0. This is when a 0 occurs more than once. It occurs all the time. So let's look at an example here. If you had a function like this one, pretty basic, and you go to factor it to get your zeros, you'll notice it factors to the same factor, and you could write that as a binomial square. So when you set these equal to 0 to get your zeros, you're going to get x equals -3 two different times. So we say that it has a multiplicity of 2 because it occurs twice. Now, that doesn't mean that the graph kind of does a loop-de-loop and hits it twice. It just means that the parabola, it hits the graph and goes back up, okay? It doesn't loop around. So you can have a 0 that has a multiplicity. It means the 0 occurs more than once, but the x-intercept only occurs once. So that's the little difference between a 0. A 0 is an x-intercept, but that doesn't mean if you have a multiplicity of 2, you have it twice. It hits it differently. So we're going to talk about multiplicities and how you can see them on a graph and how you can use a multiplicity to graph a function by hand. So let's look at this next slide. And you can read that if you'd like to about multiplicities. But it says if it's an odd multiplicity, it will cross the graph at an inflection point where the curve of the graph changes. And if it's an even multiplicity, it does not cross the x-axis. It hits the x-axis. So I'm going to kind of enlarge this guy and kind of show you what I'm talking about. So if we're just going to look at each 0 independently here. Let's look at this guy. So you can see how it doesn't cross the x-axis. It hits it and bounces right off. So when that happens on a graph, that means it has an even multiplicity. It could be a 2, it could be a 4, a 6, 22, 38, whatever. It has an even multiplicity. Anytime you see it hit the graph and bounce off. Okay? If it hits the x-axis and crosses at an inflection point, like that cubic inflection point, you can see it changes curvature here. It's curving a different direction above and below the x-axis. That's an odd multiplicity of 3 or higher. So it would be a cubic or 5th degree or 11th degree or whatever. And then if it simply crosses like that, just cuts it, normal, that means there's no multiplicity. It's not a multiple root. It's just a one simple root. Okay? So we want to be able to look at a graph and write a possible equation for it based on how it's hitting the x-axis and be able to pull those x-intercepts from the graph. Okay? So let's look at, I want to kind of do one of those first. So let's sketch a graph here. So we have an x-intercept here, we have one here, and we have one here. Okay, so if we're looking at this, we can write the equation, or a possible equation, because there's really infinite, because we don't know what the coefficient is going to be. But this is at -3. So the factor at -3 would be x plus 3. Remember, we have to go backwards. So this 0 is a -1, so the factor that gives me that 0 is x plus 1. This 0 is a 2, so that factor is x minus 2. Okay, so there's our 3 factors based on the x-intercepts. Now we're going to go back and look at how it's hitting the x-axis and determine how many zeros you actually have there. So at -3, that is just a simple cut, so that's a multiplicity of 1, if you want to think of it that way. X plus 1, and -1, it's cutting at that inflection, so that's going to be a 3, a 5, a 7. We're just going to go with the lowest possible, so we're going to say a 3. And then the 2, it's hitting the x-axis and bouncing right off. So the lowest even degree we can put there is a 2. Okay? So again, we are looking at x-intercepts, writing them as factors, then looking at how those x-intercepts, how the graph is treating them. Are they cutting through them? How are they cutting through them? And if they're not cutting through them at all, if they're just bouncing off. So we almost have a function written here. We're going to put an f of x out here. So the thing we have to look at right now is the end behavior. The end behavior is indicating that this is an even degree, and if you add up these multiplicities, you have 1 plus 3 plus 2, that's a 6. So this means this is a degree 6. Okay? It's a degree 6, but it's opening down, which means it's a negative degree 6. So we have to look at end behavior to determine if we have a negative coefficient out here. I'm just going to put an A out there. I don't know what A is. A could be any number, but it has to be a negative value there for the graph to flip upside down. Okay, so let's look going the other direction now. So here is a factored polynomial, and we're going to take each of these factors and set it equal to 0. So x plus 2 equal to 0 would give me a 0 of x equals negative 2. The exponent tells me it's multiplicity. X minus 1 set equal to 0 gives me an x equals 1, and it has a multiplicity of 2. So if I put the multiplicities together, that tells me my degree. The degree is 5. You have 3 plus 2 is 5 zeros. It is a positive odd degree. So my end behavior looks like that. It goes from low to high. And we're going to sketch it. Let's look for our y-intercept while we're looking for things. So the y-intercept, 0 plus 2 cubed, 0 minus 1 squared. So 2 cubed is 8, negative 1 squared is 1, 8 times 1 is 8. So we have a y-intercept at 8. We have an x-intercept at negative 2, and 1 at 1. We have to start low because of our end behavior. We're going to start low on the left and end high on the right. So here we go. Negative 2 has a multiplicity of 3, so I'm going to have to come up here, cross that with an inflection, hit the y-intercept, continue down, and bounce off the 0 at 1. So that's our graph. A very rough sketch, but it includes the y-intercept, the x-intercepts, and it includes any turning points it has. Okay? And shows multiplicities. So let's try another one. So our zeros, which hopefully are getting a little quicker to do. X equals 0. Remember, this x is by himself, but he's still a 0. He has a multiplicity of 1, or doesn't have a multiplicity. X equals 3 has a multiplicity of 2. If I put the multiplicity together, I get a degree of 3, and it's a positive degree 3. So we have the same kind of end behavior we just ended up with. The y-intercept is 0 times 0 minus 3 squared, which gives me 0. So we'll go to graph. You're at 0. We're at 3. The y-intercept is 0. The end behavior is starting low and ending high. So I have a simple cut. And then we come down and hit and go back up. So it's a simple root, just cutting straight through at 0, and then a double root at 3. So it's going to bounce and go back up. Again, I'm not that concerned about, how high this guy's going. This max. It could be lower. It could be down here. I'm not for certain. I don't even have y-axis labeled unless I have a y-intercept. Not as concerned about that. We're looking at turning points, like how many there are, x-intercepts, y-intercepts, in the specific way it's hitting the x-axis. Okay, so, as I said, beginning of the lesson, given a factored polynomial with exponents all over the place, you should be able to graph it. Okay? So we're going to try this one. It's a lot, not a lot bigger, but bigger. So take a second, see if you can write all the x-intercepts down and their multiplicities. See if you can figure out what the degree is and whether it's a positive or a negative degree. Not positive or negative degree, but positive or negative polynomial, leading coefficient. Figure out what the end behavior should look like, the y-intercept, and see if you can graph it. That's our goal. So my first x-intercept is at -2, multiplicity of 1. Next one is at 1, multiplicity of 3, and 4, multiplicity of 2. I add my multiplicities up and I have a degree 4. I have a negative out front, so it's a negative degree 4. So I'm just kind of putting this down to remind myself what my end behavior's got to look like. And my y-intercept, I have that a there. Let's just get rid of that and make that a -1 to make this a little bit simpler so we can actually find the y-intercept. Okay, so my y-intercept is -0 plus 2 to the first, 0 minus 1 cubed, 0 minus 4 squared. So the negative's out here, it's just going to stay out here. So we have 2, -1 cubed is -1, so that's -2 times positive 16, so that's -16 times the negative in front gives me, I'm sorry, 2 times -16. I don't know what I just said, but it ends up being 32. Okay, so here we go. We're going to plot our x-intercepts. -2, 1. Now let's say the y-intercept is higher, than what I want to graph on my graph. My graph's going by ones and it goes up to 10 or whatever. Picture your calculator screen before you zoom out or something. Sometimes it just looks like 2 lines are going off the top, and that's okay. We can do that. So let's say my y-intercept's way up here. Okay. So our end behavior says we're going to start low. My first is going to just simple cut. It's going to go up. It's going to go off. This is up here somewhere. It comes back down. At 1, it's got an inflection, turns around at some point, hits the 4, and bounces back down. So when you're done graphing, you should look at it and say, all right, my end behaviors are both pointing down. That checks. I have all my intercepts and make sure my multiplicities are hitting. If you don't hit those multiplicities right, when you're crossing those, your end behavior is more likely going to be all screwed up. Okay? So that's what you want to check. And it's okay that some of your lines are going off the graph at the top because you don't have a y-intercept within the range of what we have on our graph, and that's okay. All right, so hopefully we can do that by hand. Okay, the last part of today's lesson is dealing with intermediate value theorem, and it sounds so complicated with what they're saying. But the gist of it is this. If you have a function that is continuous, and continuous, if you remember, means there are no breaks, no breaks in the graph caused by an asymptote or a hole in the graph or anything like that. It's continuous, a nice smooth curve between this a and this b value, these two x values. Okay? If it's continuous between those two x values and the y of this first x value and the y of the second x value that we're picking, if those are opposites, like one's positive and one's negative, at some point in between those two x's, there's an x-intercept. And that sounds even more confusing even when I'm saying it. So let's look real quick at this graph. This is a picture of it. So here's my a, there's my first x, and here's my b, that's my second x. And you can see the curve is continuous. There's no breaks in between that a and b. Okay? Doesn't mean that the graph or the function can be discontinuous somewhere else, but it's got to be continuous between the two x values you're talking about. Okay? If the curve is continuous and the y value of this a is negative and the y value of this b is positive, at some point between a and b there has to be an x-intercept. You have to cross over 0. If you think of the basic number line, if you're going from a -2 with a continuous line and go all the way to a positive 5, you had to have crossed that 0 mark somewhere. So that's basically what it's saying. If you have a continuous function and you go from a positive y to a negative y, or vice versa, a negative y to a positive y, either way, you have to have an x-intercept somewhere in there. Okay, so let me show you another way. If I'm looking at a table in my calculator, and here's my x's, and then, you know, my y's are doing whatever they do. And it's hard to make up a question like this. Okay, so there's my y values. What you're looking for is, we're assuming the function's continuous. You're looking for sign change in the y values. You can see right here, the y went from a positive y to a negative y. That means there's a 0 in between -1 and 0. Somewhere there's a 0 there. There's an x-intercept in the graph. And if you continue down this table, right here's another sign change. I went from negative to a positive in the y's. So somewhere between the 2 and the 3, there's another x-intercept. There's got to be. You can't go from positive to negative and not cross 0 if the graph is continuous. Okay? Now you can if it breaks, if there's an asymptote, you can jump from one branch to the other branch, and that's not the same. Okay? That's kind of cheating. So if it's continuous, it's got to cross 0. And that's what you want to understand. So one last question, and then you're going to have some practice questions to work on. So explain why a polynomial function of an odd degree has at least one real 0. So imagine an odd degree function. Polynomials always continuous. So that already fits that first part. It has to be continuous. We know polynomials are continuous. We're good. If it's an odd degree, think of the end behavior. It's doing something like this. The end behavior here, as x is going to negative infinity, the end behavior is negative infinity. So let's consider that an x and a y. As x goes to negative infinity, the y goes to negative infinity. As x here goes to positive infinity, the y goes to positive infinity. So I have a y change. I went from a negative to a positive y here. So between negative infinity on the x-axis and positive infinity on the x-axis, there has to be a 0. Because you're going from negative y's to positive y's. At some point, you have to cross the x-axis. It's not true if it's an even function because the end behaviors are going to be the same. So they're not going to have a sign change in the y location. Okay? So you can think of this as, if I plug in negative infinity in this graph, my y value, my height, is at negative infinity. If I plug in positive infinity for my x, my height is at positive infinity. You have a sign change here. Therefore, between this a value and this b value, there must be a 0. Okay? So a lot of things to kind of muddle over today. Think about it. The main goal here is, can you graph polynomial functions that are in factored form? And you might have to factor them first before you graph them. Okay? Multiplicities, x-intercepts, y-intercepts, changes. Okay? All right, let's try it.